We've talked lately about definite integrals giving some quantity that applies to a real life situation. In this preview activity, we're going to explore one such integral and we're going to do something a little different for it that we haven't done in previous integrals. We have a company with a large customer base that has a call center that gets thousands of calls a day. They study the data for how long callers wait for assistance, and they determine that this exponential function models the time the customers have to wait, where the fraction of customers who wait between A and B minutes, where t is our time variable, is given by the integral from A to B of this function p of t dt. That's their model for how much time the customers wait. So using this model, what fraction of callers are going to wait between 5 and 10 minutes, remembering that 5 and 10 are values of t. What fraction of callers are going to wait between 10 and 20 minutes? And then what about the fraction who wait up to a certain number of minutes? So from 0 to some number of minutes. That's what these parts are going to have you examine. Then capital F of B is going to be the fraction of callers who wait between 0 and B minutes. In other words, instead of both of these being numbers, we're going from 0 to B. They're asking you to find a formula for f of b that involves a definite integral. So you should be able to see which definite integral they're talking about, and then use the first fundamental theorem of calculus. In other words, calculate the integral, thinking of b as some sort of number, without knowing what the number actually is, to find a formula for f of b that no longer involves a definite integral. In other words, calculate the integral. Once you've calculated that integral, you should have an expression in terms of b. And the last part is, what if you took the limit as b goes to infinity of f of b? So just calculate that limit, but then there's more. What is its meaning in the context of the problem? What does it mean to let b go to infinity? So try that on your own. If you haven't already paused and tried this preview activity on your own, please do so. It will help you get more out of what comes next. Okay. So the topic at hand is improper integrals. There's going to be two types of improper integrals we're going to talk about, and we're going to talk about what an improper integral is. Why is it called improper? So the first type is the one where you have unbounded intervals. Okay? If you think about taking an integral that has some letter as one of its bounds and letting that letter approach infinity, kind of like what we did in the preview activity, we want to remember what that means. We want to think about what that means, and we want to figure out a way to calculate it. So if you look at the text, before the preview activity, there's an example about light bulbs. And what it says is, if I want to find the fraction of light bulbs that fail eventually, we're taking the limit as b goes to infinity of the integral from 0 to b of this function. The other way to write this that you'll see is integral from 0 to infinity of a function. Now remember, infinity isn't a number. So we can't just do this integral like we normally would and then plug in infinity. It doesn't actually make sense. And we'll see why doing that doesn't work in some problems. Even though you might think it's an okay technique, it definitely won't work in all problems. It's just a notation we use to represent what's up here. Calculating an integral with a limit of integration that's just some letter, and then letting that letter go to infinity. Okay. So again, this first type that we're talking about is unbounded interval improper integral. So if we look at what happens, we have an area that's going in this example. Picture it's going from 0 to b. In other words, it's integral from 0 to b. We don't know what b is. It's just some point on the t-axis. When we let b go to infinity, what's happening is we're letting this endpoint here, this edge endpoint, letting it go all the way to the right. That's what these 3 dots mean. The question then is this area that's extending forever and ever to the right, is that area actually equal to a number, a solid finite number, or does it just keep growing so much that it's infinity?